second talk is by Prerna Sharma on chiral membranes and rafts.
Right. Oh. So, good morning, everybody, and it's an honor to give this talk. The title of my talk is Chiral Membranes in Rafts. I have recently started at Institute of Science as an assistant professor, and so the contents of this talk are basically my postdoctoral work at Brandeis University with Professor Zvonimir Logic, and Thomas Gibault and Andy Ward were my co-workers in this work. So the pictures in behind this title slide are basically membranes or sheets which have rippled edges, and I'm going to spend some time telling you how chirality can influence the shape of these membranes, and then tell you how it can also be used to assemble finite size clusters as shown over here. So rippled edges are quite common in nature. So you can do a simple experiment of taking a garbage bag and just tearing it, and what you would find is that the torn edge spontaneously buckles out of the plane to make this wavy edge. You can also find them in natural settings like ruffles of dandelion flowers. And the common feature in all these three pictures is that you have thin continuum elastic sheets which undergo buckling instabilities under deformation. And one of the ways to characterize this buckled state is to measure what is called Gaussian curvature, which is the product of two principal curvatures. And in all of these examples, the Gaussian curvature is negative. And a negative Gaussian curvature has certain significance associated with it, that it typically means that you have a minimal surface, which is zero mean curvature. So the question that I was interested in was how can I tune the curvature of self-assembled sheets by playing around with the geometry of the building blocks. And one of the most important self-assembled sheet in life is cell membranes, and it's made out of lipid molecules which have a hydrophilic head and a hydrophobic tail. And if you have many such molecules in water, they spontaneously make these bilayer like geometry where the hydrophobic tails are shielded from the unfavorable solvent. And it's known that curvature mediated interactions play a major role here. And the system is quite complex because it's made out of a large number of lipids and proteins. And a highly controversial subject in membrane biophysics is the existence of what is called lipid rafts, which are clusters of lipids and proteins embedded in this membrane. And people believe that the overall curvature of these sheets could also influence the assembly of rafts. But it's really hard to study the system experimentally because the thickness of this sheet is only a few nanometers and the dynamics is really fast. So as soft matter physicists, we like to scale up things, and we have done that in the past with great success. For example, instead of studying atomic crystal, we have invested in studying colloidal crystals where you have scaled up by 3 orders of magnitude, and great insights have been obtained in the fundamentals of crystallization and nucleation and things like that. So the question is there something similar we can do for the case of lipid bilayers? Meaning, can we assemble a two-dimensional sheet whose thickness is about a micron instead of a few nanometers? So this mapping or this scale up was figured out by Zvonimir before I entered the lab, and this is how it works. So the building block of these micron thick sheets is a virus, and it's a rod-like virus which has a length of about a micron and diameter of a few nanometers. And these are chemically homogeneous, so it's the exact same protein all over the rod. They're highly monodispersed because they are viruses, and we have a library of them where we can change their aspect ratio, rigidity, and chirality, and I'll describe what chirality in this context means. and in the bulk they form liquid crystalline phases. So if I have just a dilute solution of these rods, they interact through screen Coulomb interactions, and there is no possibility of any structure formation. So to make a condensed structure, we introduce effective attractive interactions using depletion attraction. So in the scheme of things, we mix the rods with non-adsorbing polymer coils. So the blue things are the coils, and the red sticks denote rods. Now each such coil is excluded from a zone around the rods, and if the rods come closer than a coil diameter apart, then some free volume becomes available to the polymer coils, and that lowers the free energy of the system, because it's the entropy of the polymers that really matters and not so much of the rods. Yes?
Sorry, quick clarification. So you said these interact with screen Coulombic.
Yes.
So these are charged?
Yeah, these are highly charged rods. So you put in salt to screen that much repulsion. So the nice thing about depletion attraction is that we can independently change the strength of the attraction by changing the polymer concentration, and the range of attraction by changing the polymer size. So when I mix these rods with the non-adsorbing polymer and inject that solution in a glass chamber, this is what initially we would see, that a few rods come together and make these little discs. And if you look at the disk from the top, it will appear as a circle, and if you have an edge on view, it will appear as an ellipse. And then what happens is that they start coalescing and making larger disks. So in the end, you can end up with really large monolayers, tens of microns in diameter, one rod length thick. So on a good day, on a good sample, this is how the sample chamber looks. Lots of these monolayers floating on the glass surface. And here I am going to switch from bright field to fluorescence, where 1 out of 10,000 rods have been labeled, and they are pointing at us. So these are individual rods freely diffusing within the membrane. And these sheets have long wavelength elastic properties similar to those of lipid bilayers. So we end up calling them colloidal membranes, because they have these minimal properties of fluid-like order within the membranes and long wavelength elastic properties. So one important aspect of these building blocks is that the rods are chiral. So by that, what I mean is, if you zoom into the ultrastructure of this virus, you would find that the coat protein is helically wrapped around the DNA, and that leads to what are called chiral interactions, in which two neighboring rods don't want to be perfectly parallel with respect to each other, but rather want to maintain a preferred angle with respect to each other. So when you make these bulk pneumatic suspensions, what you find is that it's not a pneumatic, rather it's a twisted pneumatic, where the director rotates. So this is how, so in the case of the wild type virus, the director rotates in the anti-clockwise direction. And as I had mentioned, that we have a number of mutants. So we have a mutant whose aspect ratio is exactly the same as the wild type, but whose the chirality is switched. In other words, it will make a cholesteric of the opposite handedness. So now this tells me that if I start mixing these two kinds of rods, there must exist a concentration where I will have a racemic mixture, so that the overall chirality cancels out, and indeed that happens. So in this set of pictures, I am changing the concentration of one of the rods, and so if it's purely FDY21M, which is the right-handed virus, you get a cholesteric which you can image through cross polarizers, and so the spacing between these fringes gives us the pitch of the cholesteric. And then as you start doping it with the FD wild type, which is left-handed, the fringes disappear, which means that now there is no twist associated with the system. And then eventually on if you go back to the pure FD wild type, you get back the pure cholesteric phase. And the pitches of the two kinds of viruses are quite different actually, and that's why the racemic mixture is not half and half. It's at 20% FD wild type and 80% FDY21M. And so this plot shows how inverse of the pitch varies as the fraction of one of the rods, and we go from right to left-handed going through a chiral system. So if I think about membrane assembly from chiral rods, so initially a few rods come together and make this cluster. So if the system is achiral, then more rods can keep joining and I'll make an infinitely large monolayer. But if the rods are strongly chiral, then the next set of rods would be slightly tilted with respect to the initial cluster, and then it will be even more so, right? And so the fact that the rods are chiral sort of lets me into trouble in the sense that the tendency of the rods to twist is incompatible with the formation of large monolayers, meaning the next layer would turn even more, and instead of getting a flat sheet you would get a twisted ribbon. So there are two possible outcomes as to how the system resolves this frustration. One is that I can do this kind of thing in many parts of the sample and get self-limited membranes, or that the rods untwist in the membrane bulk and expel the twist to the edges, because at the edges they are free to twist. And it is the second route that our experimental system takes. And this expulsion of twist has one-on-one analogy with how a superconductor expels magnetic field, and that was figured out by Digens. So, and so we can visualize the tilt in our system using fluorescence microscopy. So here again 1 out of 10,000 rods are labeled. So in the middle the rods are pointing at us, but at the edges you can see the entire labeled rod. But in order to figure out what is called the twist penetration depth, or the length scale over which you go from a perfectly tilted rod to all the way a standing straight rod, we use quantitative polarization microscopy, in which the pixel brightness is proportional to the local tilt of the rods. So it's really bright at the edges, means the rods are tilted with respect to the layer normal at the edges. And then I can take a radial cut to measure the twist penetration depth, which is about half a micron for our system. So as I had mentioned that we can have both kinds of viruses, left-handed and right-handed, and how does that change, how does that determine the handedness of the edges of the membrane? So the two-dimensional pole scope doesn't let us know the direction of the tilt, whether it is clockwise or anti-clockwise. So to figure that out, we use what is called a 3D pole scope, in which the membrane is divided into an array of these disc-shaped objects, and each disc represents the local birefringence or the local tilt as a function of direction of the light rays that enter that local part of the sample. So here in this small picture, the zero retardant spot or the zero tilt spot is at the center, but as you go towards the edge of the membrane, the zero retardant spot is off-centered, and the azimuthal position of this maximum tells you whether it is clockwise or anti-clockwise. So if you do the same imaging for the virus of the opposite handed virus, what you would find is that now this is exactly 180-degree flipped. And so what this tells us is that the microscopic chirality of the rods governs the macroscopic chirality observed at the edges of the membrane. So a left-handed virus gives a left-handed membrane, and a right-handed virus gives a right-handed membrane edge. So the experiment that we set out to do was to ask the question that what happens if I take a membrane made out of purely left-handed rods and a membrane made out of purely right-handed rods and have them coalesce. And this is what happens. So they come together and make this snowman kind of object. And so this sort of video of course shows that we can now start to self-assemble edges which are rippled, but also raises a number of questions as to do the two kinds of rods remain phase separated, or are they completely miscible? What is the structure of these two cusps, and how do they interact? And so these are some of the questions that I am going to answer in the next few slides. So we do our favorite technique of looking at the tilt of the rods around this cookie shaped membrane. Is so you do a polarization microscopy imaging, and what we find is that there is tilt everywhere except right at the cusps. So at the cusps, the rods are along the z axis. In order to know what is the handedness between these two regions, we do the 3D polarization microscopy and find that there is left-handed twist, which then turns into a right-handed twist as you go across the cusp. So the cusp is basically separating regions of opposite handedness, and as a result they have to appear in pairs. Isolated cusp cannot exist because of the circular geometry that we have. And here also it is quite evident that the rods exactly at the cusp are along the membrane normal. So to understand this phenomena of rods at the cusp, being along the z-axis, we took z-stacks and realized that the cusps are not in plane. So they are actually alternating up and down as you scan the z direction. So basically what's happening is that the region near the cusp rises from the plane to reduce the tilt orientation mismatch. So if you are in the plane, they have to be like this, which is a huge energetic cost, compared to if we go above the plane as shown in this schematic, then the rods can almost be parallel, and then the orientation mismatch is minimum. And because each cusp separates regions of opposite handedness, in order to maintain the preferred tilt, the cusps have to alternate above and below the plane. And this sort of geometry gives a negative Gaussian curvature, which then stabilizes the increase in the edge energy. So by going out of plane, I've increased the amount of edge I have, but then because of the negative Gaussian curvature, that sort of offsets the increase in edge energy. So the phase diagram of these ripple membranes is sensitive to the amount of, yes?
Inside it's mixed up, or inside also there is a segregation?
Yeah, I'm just going to show whether the rods are segregated or not. So the phase diagram of ripple membranes is a function of the volume fraction of one of the rods and the polymer concentration. And if you are away from this achiral regime, then you get these flat membranes with round edges, and the two kinds of rods in the fluorescence channel are uniformly mixed. As we go towards the chiral regime, achiral regime, we have these ripples of opposite handedness, and what's interesting is that the two kinds of rods are completely mixed. So there is really no phase separation either at the edges or in the bulk of the membrane. So it's some kind of overall chirality or achirality that sets up and then leads to these kinds of structures.
So how do they increase the number? Earlier you showed just a cusp.
Yes. You can just have sequential coalescence. I mean, when we make these samples, we just mix the two kinds of rods, add the polymer, and let the self-assembly proceed. So then as you add more and more discs, you can, each time you add more discs, you get a cusp, a pair of cusps. Yes?
What's the size?
I will come to it, but it's basically a competition between the bending energy. So there is some sort of bending energy associated by this cusp, I mean this rippling, and then the line tension of the cusp. So square root of k over gamma gives you a length scale which roughly matches with that. And so let's zoom into this achiral regime, and exactly at the achiral limit we have these cusps which are of similar lengths. But as we go away from this limit, the regions of opposite chirality now become much smaller. So now you have a very small left-handed and then a large right-handed region. So we can tune the spacing between these defects as we change the strength of the chirality. So as I make the system more and more achiral, it costs me a lot of energy to twist in the wrong direction, right? And so, yes?
So when you said you had the sequential addition, so
yes.
I mean every time you had, let's say that opposite sides,
right,
the central, the first starting membrane, you're going to have twists in the opposite direction.
yes.
Why can't you just come around the periphery, meet so that we just have one twist? So why can't the drops go? The FDY, the FD,
yes.
just come together, cancel the twist so that there's just one pair of twists at the end of the day.
I didn't get the question.
So what I'm saying is every time you're going to put in, bring the FDY and the FD,
yes.
you're going to introduce a pair of twists.
Yes, yes.
So why can't it be that one pair just, so annihilates the other one so that you just left with one pair of, at the end of the day, instead of having two pairs, you just
yes.
have one.
Annihilation actually is a very difficult process, because to annihilate you have to bring them close enough, right? And that costs a lot of bending energy of the, yes.
Another possibility, if you look at this total diameter,
Yes.
that length is much smaller than the pitch. Right?
So
therefore, it has to at least make several pitch to have this kind of. So what I'm saying is the size of this droplet also matters.
I mean, the size of droplet is macroscopic.
They're bulk colosteric, right? If you have a thick sample, then pitch has to have several times when to match the surface.
Yeah, I suppose. I think I probably we can talk more about this as fine. So so far all the pictures that I've shown you is self-assembled in the way that we mix the rods with the depletant and put them in the glass chamber and look at them. But and that was mainly by mixing two kinds of rods of opposite chirality. But even with single rod system, if the line tension is low enough, you can get spontaneous creation and annihilation of ripples. So in this system here, just the fluctuations of the edge are so enormous that there is a spontaneous creation of a small defect. And similarly here, they just annihilate themselves. And so in this system, there is no opposite chirality. It's just membranes made out of a single rod type, except the fact that now the rods are so small that the line tension has dropped enormously. So, so basically, at the edges, the rods are going in, let's say, in one sort of direction. Now, the thermal fluctuations are large enough to cause a local region to flip the other way around. And when you do that, you will get these two defects. So typically in liquid crystalline systems, this spontaneous reversal of the tilt is never observed. So in fact, so this is a very unique system to show that. And so.
In this case, with thermal fluctuations, these defects won't be created in pairs.
I mean, they are a pair, right? So like this cusp, when I say, I mean, each ripple has two cusps at its end. That's the pair I'm talking about. Right? Yeah, it's purely because, so this is what I was trying to say. That you have this, let's say you just have, oops, that was a very bad drawing, but you have a left-handed region which separates right-handed on both sides, right? As soon as you have a region which becomes left-handed, it will have right-handed on each side. So this pair, so it's a pair of defects, right?
So the defects are kind of diffusing.
The defects can diffuse if you just have a pair of defects on a large membrane. But I mean, they can,
No, I'm saying on the line.
yes.
They are kind of diffusing, and then when they meet, they can annihilate.
Yes, yes. And I think that's what Rajesh was asking me, that why can't they come together? But yeah. So that's in the very low line tension limit. So most of the data that I've shown you is in the high line tension limit, where that's not, or no, actually high bending rigidity limit, meaning if you want to bring these 2 points close, then this part has to bend quite a bit. And so the bending rigidity scales with the rod length. So the most of the data that I've shown you was for about a rod length which was 0.8 microns, and this spontaneous data is at like 0.4 microns, so half the rod length. What do you mean by that? I mean, it's a droplet, which it's a rod polymer interface meeting just the polymer solvent. So it's the way you define the definition of line tension is exactly the same as you would have for, let's say, a 2D droplet of oil in water. So yes. No, in coalescence it doesn't really play a role, but in spontaneous creation or annihilation, in case you just have only a membrane made out of only chiral rods, one component system, and you lower the line tension enough, then you can switch a local region of the edge to the opposite type, and that would lead to a pair of defects as shown here somewhere. So that's all I'm trying to say. Maybe this was too confusing. Right. So in equilibrium, so there is some sort of equilibrium distance between the pair of defects, as Guru had asked. And with traps, we can sort of push them or pull them around and ask the question that are these defects a bound pair or an unbound pair? So if I'm in the perfect achiral limit, it shouldn't really matter if I change the distance between the defects, because I'm not really paying any energetic penalty. On the other hand, if I'm in the chiral limit and if I try to stretch the region of the wrong-handedness, then I'm paying a large energetic cost. So there are two contributions to changing the equilibrium distance between the pair of cusps. One is the energy associated with the curving the interface if you try to push the two cusps together, and the other one is the fact that the line tension itself is dependent on the orientation of the rods, or the preferred orientation of the rods. And yes.
So I understand this video. So what you have is the thin line is the membrane.
Yes.
Holding one trap fixed, just pushing onto the membrane wall.
Okay, so I didn't explain so I was going to explain this video. So we want to measure the interaction between these two defects, and what we do is we put beads in between that space. So because it's sort of like a dip, so we can just put a bead there, and we hold one of the bead constant, and the other one we move at known separations, and then measure the force on the static one. This video just shows that we can really push the defects together.
So,
Yes.
how do you measure the stiff forces?
So I mean, it's sort of technical, but what we're really doing is that we know the trap stiffness here, and at equilibrium we measure its fluctuations, and we know, okay, this is the center position. And then as I move this trap further or lower, it gets pushed from its equilibrium position. And then you just do.
How do you move it? Just by a mirror or by?
We were using AOD, so with AOD you can move it
That
easily.
changes the power also, right?
Yeah, so that's why I said it's a technical. So this measurement wasn't a very straight. We had to worry about a lot of the things. So this is how the data looks. So for the achiral membrane, as I mentioned, that there is really no line tension like penalty. If you are in the achiral limit, I can just stretch or stretch as much as I like, and so the force is nearly zero. And that was another major technical difficulty. How do you call a zero force? I mean, how do you measure so-called zero force? And these dark lines are the point where the equilibrium distance of the cusp exists. And then as I try to push the cusps together, then I have to pay this enormous bending rigidity cost. And so, so then the bead gets pushed. So, so one is the positive force, and then there's a negative force. So, which means that the bead tries to, as I try to bring this guy closer, the bead sort of gets pushed in the other direction. So what I have shown so far is that tuning the chirality leads to a robust way for self-assembly of membranes with negative Gaussian curvature, and that comes through the fact that you have regions of opposite-handedness that end up in a pair of point defects which undergo bound to unbound transition as a function of overall chirality. So going back to my favorite schematic, which is of that of a cell membrane, and I have shown you how we can change the overall curvature of our colloidal membranes. Another important aspect of these membranes is what I had talked to you about of the existence of finite size clusters. And so people really want to understand how lipid rafts of finite size clusters are formed in two-dimensional geometries. So to mimic something like this, or to come up with a mechanism that might be relevant here, we need to introduce some sort of compositional heterogeneity, correct? And so we do that by adding another rod length. And so now I start making bidisperse colloidal membranes where the aspect ratio of the two rods is not same. So there is a length difference, and so there are two possibilities just based on based on entropy and enthalpy. So if you have weak attraction between the rods, which means a lower polymer concentration, then entropy tells us that the two kinds of rods should be completely mixed, because then the entropy of mixing is enhanced. And then in the strong attraction regime, it's best for the two kinds of rods to phase separate, because that's when the polymer gains the maximum entropy. The depletion interaction is best satisfied under these conditions. So the two kinds of rods that I was using has two different rod lengths. So and the difference in the lengths is about 26%. They have exactly the same diameter, and they're oppositely handed, and they're slightly different in their flexibility. So indeed, we did see these two regimes, and in all the movies that are to follow, only short rods are labeled, and these fluorescence pictures have been false colored. So the yellow and red doesn't really mean anything. It's just intensity fluctuations. And then we also found the bulk phase separated regime, where all the short rods are in this one large cluster and the long rods are in the background. So in the fluorescence picture, the long rods are not visible because they are not labeled. So at this point, it looked like I can just turn the crank, I can change rod length and measure the surface tension between the two kinds of rods and things like that. I mean, it just looked like a classical phase separation phenomena, except that when we tried to look between these two regimes, meaning at intermediate polymer concentration, we found something beautiful. And this is what we saw. So this is a membrane made out of mostly long rods, fewer short rods, and almost all the short rods are in these two clusters. And they have a very well defined diameter of 2 microns. So these are finite size clusters, and you could wait like a day, a week, months. These clusters will not change their size or shape. They're going to stay exactly like this. And what you're looking at schematically is a sheet which has these two dips, and these dips are quite stable. So and these membranes were assembled again by mixing the two kinds of rods, adding the depletant and letting them self-assemble on the glass chamber. So this begs a question: is this state a ground state, or is it a kinetically arrested metastable state, meaning is it that the repulsion between the clusters is so strong that they cannot coalesce and make one large cluster and go to the bulk phase separated limit. So to answer that question, we did the same coalescence experiment, except now I have a disk made out of purely short rods and a disk made out of purely long rods, and I have them coalesce. And as I had mentioned in the beginning of the talk, we do get these two cusps, right? So these are the familiar cusps that I have talked. And we have this uniform interface between the two kinds of rods. So now they're not completely miscible. And it looks like it's just going to sit there and fluctuate. Except if you wait long enough, this is what happens. It destabilizes, and it destabilizes into these clusters of roughly the same size connected by thin bridges, which then break due to thermal fluctuations. And so this movie is sped up by quite a bit. So it took us half an hour to go from a clean interface to an interface which has these droplets. I mean, I can tell you the numbers for the two different kind of rods, membranes for each of the rods, but I cannot tell you the line tension of this interface, if that's what you are asking. Is that what you were interested in? Yeah, I really don't know. Probably it's negative because it eventually just breaks up into droplets. But it's really hard to analyze these fluctuations primarily because it was just so unstable that it would just break apart. You start going into the early stages of breaking apart. And so let's go back to the fluorescence picture. And because of the lighting, it's not quite evident, but there is a fluorescence signal in the background as well. And what that means is that the short rods are present both in clusters and in the membrane background. And we can illustrate that by using what is called fluorescence recovery after photobleaching. So I take a laser just like this one and shine it on a cluster, and that photobleaches the rods within this cluster. And then watch the system after I have photobleached it. And once we do that, so here is my laser, and so now this cluster is now totally dim. And over a span of few minutes, we would find that this cluster will recover its intensity. So what's happening is that the bleached rods come off of the cluster, and the unbleached rods from the membrane background hop onto the cluster and make it fluorescent. And this rod exchange is actually quite critical for the existence of the monodispersity of clusters. For example, I can take the system highly out of equilibrium, in the sense with using optical traps, I can chop up some clusters and merge others. So I can artificially make a polydisperse size distribution of rafts and ask the question, how does the system evolve? And this is how it evolves. So here is a cluster highlighted in red. It's very small, and it's going to shrink. Actually, it's going to lose all of its rods. And that's due to the classic nucleation issue, that if you're smaller than a critical size, you just don't exist. And then the green one is right now doesn't fit its circle, and the magenta one fits its circle. So over the span of 19 hours, the smaller one would grow and the larger one would shrink. And what's really remarkable is that this recovery to the monodisperse size distribution is purely through exchange of rods, that at no point they coalesce. And so the exchange is really crucial, that the larger ones will shed the rods, and those excess rods will then go in and become part of the smaller ones. Yes?
So in classical nucleation theory,
yes.
Once you cross the free energy barrier, you just go downhill.
Right, but here right. So here there's a backup. Yeah, so I will come to it. So I'm just illustrating that there is a rod exchange. So these clusters are analogs of 2D micelle-like systems, that they have a well-defined size and they can exchange the contents among themselves. And so this video was recorded using an autofocus microscope so that we could watch it long enough in a
all of them will have the same size.
Yes,
and,
yes.
Then there's no exchange.
And then there is an exchange, but there is a dynamic equilibrium. Yeah. So, so by quantitatively analyzing these two sets of experiments, so this is what we started off with, and this is what we ended up with, right? So there's a remarkable recovery here, and by quantitative analysis, so there are two rates associated with the system: the rates at which rods come off of the clusters, and the rates at which rods hop onto the cluster. So by writing simple rate equations, we can figure out these rates and then go to what Shreyas was saying about free energy landscape of the system. So, but I'm not going to show you that procedure because it's quite elaborate. So as Shreyas was asking, what sets the size? Why really should it stop? And so to answer that question, we just, we were admiring these membranes with lots and lots of clusters. And what we see is that they don't come closer than a few cluster diameters apart. So these are really long range interactions. And we felt that if we measure the interaction potential, maybe there will be a hint as to what's going on. And we did measure the interactions using blinking optical trap technique. In this technique, what we do is we take a pair of optical traps. So these clusters are repulsive to optical traps, so we cannot really hold them, but we can push them. So we have these two snow plows, and we'll bring them closer than what they would normally approach one another under equilibrium conditions, and then switch off the traps. So this is the video. So we're going to bring it together, much like herding them together, and then we switch off the traps. And what's going to happen is they will fall apart slowly under repulsive forces and as well as Brownian motion. And this technique is a very well understood technique in the context of colloidal particles, and we just translated it to our system. Yes?
Do you observe any kind of optical binding happening here when you get them so close? Some optical binding effect here?
I don't know. I mean, we switch off the traps beyond.
When you are
When we are holding them, it's really hard to hold them. It's almost like, we go to like 5 watts of laser power and still struggling to have them exist there. And so this is how the interaction potential looks as a function of surface to surface separation. So it's a really long range potential, so that on contact it would be hundreds of kT if I just keep extrapolating the data. And an exponential seemed like a good fit, about half a micron of range. So this half a micron is quite critical, meaning remember the twist penetration depth was also half a micron. So the answer lies there, and so we just imaged our clusters under polarization microscopy, and we find that there is twist at the edges of each of these clusters. And so this tells you why they are repulsive, because if you try to bring two clusters close enough, then the rods at the edges have to untwist, and that costs energy and leads to repulsion. Another way to understand energetically is that if the two kinds of rods were uniformly mixed, then there is no way that they can twist in the bulk. Yes?
So if you were to enhance membrane fluctuations, you will get coefficients.
If I can enhance membrane fluctuations, yes, but it's too hard.
No, so I don't know if there's a control that will drive you there. But
If you decrease the length of
If I decrease the length of
the rod,
the rod, yes, I mean we get polydispersed clusters which can then coalesce because they're not so repulsive. Yes?
what is the typical size of those?
The clusters is 2 microns in diameter.
What is the pitch?
No, he's asking the pitch. Pitch of which one?
That we have a pitch, right? I don't
Yeah, I mean, so these are two oppositely handed rods, and they're.
What is the pitch of that each?
So the pitch of the longer rod is, so the shorter rod is somewhat less chiral than the longer one. I don't.
What actually what I'm saying is that if the pitch is shorter than this size diameter, usually they have to generate some kind of defect around the perimeter.
No, the pitch is certainly not smaller than the diameter. The pitch is quite large.
In that
Yeah.
case, apart from
Yeah,
this
yeah.
interaction, we would have defect mediated interaction which is known in the
Right, right. So these are repulsive interactions. So most defect mediated interactions are attractive, right?
No, the defects of the actually.
Right, but the pitch is quite large. It's tens of microns, if I remember correctly. So correct. So if the two kinds of rods were uniformly mixed, then the rods have to stand straight because of the huge depletion attraction acting on them. But if they partition into these clusters, then there is, because of the height difference, there is a region where the rods can gather twist. So this is the golden opportunity to gather twist at each cluster size. So it's almost like how flux lines penetrate type 2 superconductors. And the fact that, I mean, at some point you can't go smaller and smaller, because at some point if you approach the cluster diameter to be of the order of rod length, then the rods have to bend around the cluster, and that's quite costly. So there is a natural barrier as to how small you can go.
Give some triangular lattice of this flux.
I will show you. So so this is what, and the fact that they're oppositely handed is quite important, because what's happening is from the center the rods are standing straight, and then as you go towards the edge, the shorter rods twist this way, and then the longer rods can then just uniformly twist back. So there is no defect at the edges of the clusters themselves. And quantitatively we do the same thing, take radial cuts across the edges of the clusters and measure the amount of the tilt and the twist penetration depth. So this is plotting the retardance as a function of distance from the center of the cluster. And quantitatively what we see is that larger clusters have more tilt associated with them. So there is more signal, but the twist penetration depths remain similar. So the twist penetration depths shown in the red are quite similar, and the tilt goes up. And so if the hypothesis of repulsion is correct, that it is because of the tilt of the rods, then the different sizes should have different strengths of repulsive potential. And so we repeated our experiments for 3 different sizes, and this is what we see, that the larger cluster size is of course more repulsive than the smaller one for the same surface to surface separation. And we can sort of collapse this data by scaling with the magnitude of the twist. So there are no fit parameters here. I just picked up the data from the polarization microscopy and divided it on the y-axis to scale. So having understood how this repulsive interactions come about, we can now start to look at higher order assemblages with them. So if I have low number density of these clusters, they have dilute liquid like order, where the pair distribution function just rises and then settles out quite quickly. As I increase the number density of clusters, short range order sets in, and I get beautiful peaks at each each ordered region. And at the highest number density, I get hexagonal lattices with regularly spaced peaks. And though in appearance this looks like a 2-dimensional colloidal crystal, it's actually a lot more in there, because it's a crystal where I can bleach each particle and let it recover. I can chop any particle at will and it will come back to its size. So it's a very soft crystal where its constituents can grow, divide, appear and disappear. Yes? I'm sorry?
Oh, that is R.
Yeah, that's R. Yeah. So,
Going from 1 to another, is it
yes.
a distance
Yes, there has to be. I mean, there is a liquid to crystal transition.
So is it somehow, same context, is it somehow not similar to that, like you have a type 1, type 2 superconductor transition where you have in the type 2 phase Fox conductor triangular lattice of those flux lines?
Yeah, that's what I said. The formation of clusters is like a type 2 superconductor where the twist is.
So you are going from type 1 to type 2.
But I mean, all of them are type 2. I will not say that this transition is type 1 to type 2. I mean,
Here I see kind of triangular lattice, but here the dilute one.
yeah, the dilute one, but what I'm claiming is a type 2 like superconductor is the fact that you have clusters in the membrane bulk.
But in type 2 also, when they penetrate, they also form this triangular lattice, right? The plus lines.
If you have, I mean, if you have large number of them, I think it's dependent on the
It also depends on density.
on number density. Yeah. Yeah, and it's also a very powerful self-assembly because each cluster has about 20,000 rods. And so with relatively very little effort, we have put together 20,000 rods in a cluster with an error bar of maybe 1,000. Right? So that's it's a highly monodispersed system. So to summarize what I have done pictorially is I started with some rod-like colloids. I added polymers to make membranes, and then I doped them with shorter rods to make analogs of 2D micelle, which I then put back into colloidal crystals. And so now I can technically stop my talk, but I'll take 5 more minutes to show you that that it's not that I took 2 rods which were highly tuned to see all of this rich phase behavior. It's quite robust, and we have done it for, as I mentioned, we have a library of these mutants, so we can just pick any at our will and ask the question whether we get finite size clusters or not, and we do. So the rest of the talk is all about stuff that we don't understand at all. So it's just to show you the diversity, the richness of the system. And so in this set of movies, what I'm doing is I'm growing this cluster. So I'm adding more rods to it. And it's not the same cluster that I've shown you through this entire talk. So it's a different rod combination. And it's a small cluster, so it's, it's happy there. And as I add more material, it just becomes bigger, and it's doing very large fluctuations in shape because it clearly is a low line tension cluster. And then I add more, and it just looks, it grows, and it's still it's going to these stringy like configurations, but on average still coming back. And then there is a shape transition. So it no longer wants to be a circular cluster, it becomes a horseshoe. And so this is quite non-intuitive. If I have just a normal water droplet, I add more water, it just becomes a larger droplet. But here, instead of making a larger circular droplet, I'm making a horseshoe, which can then grow and become a thicker horseshoe. And if you keep going, it eventually closes onto itself, like here. Right, so it's an annular cluster, and this cluster loves to bind to a small kind of its own. So it's a lock and key kind of arrangement where this cluster is not going to go anywhere because the horseshoe has latched onto it, and it's not latched onto it in real sense, meaning there's no physical contact. It's just through membrane mediated interactions that is happening. And then if you have these 2 droplets by themselves, they're happy, they're circular. You place them next to each other, and they want to be an effective horseshoe. So, we also stabilized the bridges that I had shown in the coalescence movie. So now we can start to make molecules, monomers, dimers, and trimers. And this one is my personal favorite, which is bead on a chain kind of cluster.
How are these different from the previous ones?
So in this one, I have changed the strength of attraction. I've added more salt and polymer concentration. And here, it's a totally different rod combination. The chirality difference has been changed, essentially. The delta L by L stays the same. I'll just leave you with the picture of all the interesting things we have seen which is this. And so, here we have these horseshoes which repel each other, a lamellar phase, a polydispersed cluster phase, a square lattice, and so there's a lot to really explore and understand here.
So
Yes.
is this closing are these closing going into vesicles?
Yeah, so these are analogs of, these are 2D vesicles essentially. Yeah, yeah.
So if you add enough material, you can change these sheets into vesicles?
No. So here actually the background is short rods, and these green things are the long rods. So this is not a one component system. But I think what you are asking is, can we make vesicles?
Because is there a size limit?
So this vesicle aspect is, so the rod length is quite large, about a micron. So you would imagine that if you cannot grow infinitely large sheets, because that is just a lot of edge energy, and so that's why vesicles form. But because the thickness is so large, the bending energy is very high, so they are sort of left in these semi-infinite states. If you reduce the rod length, we have seen signatures of vesicles, but they're not very clean as of now. So you mean this one? So
These look like onions.
right.
Looking at a cross section of
Yeah. So this is 2D onion vesicle, and it's, I mean, this is how it self-assembles, and I don't understand why. Right.
Does it automatically?
Yeah, I mean the internal O is automatically, and the next O's were somewhat directed, with the optical traps we made them. But the inner O is definitely self-assembled. Yeah, and everything else is self-assembled. Yeah, and so to conclude, what I have shown is that chirality is a robust way to self-assemble ripple membranes, and that the minimal elements of length by dispersity, chirality, and shape anisotropy are enough to give me finite size clusters, and to show you the fact that we can engineer Gaussian curvature even more. So going from ripple, we can now make 3D structures. So we can make what are called catenoids. So a cross section of catenoid looks like this. So we have
They're freestanding?
yes. So right, because these are proteins, so they're not very heavy. The weight is not collapsed. Yeah, and in sorry, I didn't put scale bars. So this is one rod length. This is one rod length.
So this height of the
Height can be quite large, 10 microns. Yeah, so they're very big. So they don't like go.
they can't really do.
They can do cubic phases if that's what you're asking. We can make cubic phases now, like with 3 of these pipes. Oops, what happened? I think I just pressed the, all right. So this is actually 3 of these in a, so that's a 3 pipe system. So there's nothing prevents us to go to n pipes. It's just it. Yeah. It's just it's very complex to look through in the microscope. And in the end, is this at all relevant to cell membranes? That's what people asked us when we showed finite size rafts. And I think it's really one of the mechanisms that might be relevant to cell membranes, because so it's known that cholesterol is a very key component in formation of lipid rafts. And cholesterol is a chiral molecule. In fact, that was the first chiral molecule identified in liquid crystal physics. So what all we are saying is that maybe it's important, but in a system as complex as cell membranes, it's never one thing that really leads to a particular phenomena. So it's always a confluence of hundreds of effects, and this is one of them that might be relevant. So with this, I can thank you for your attention. Do
In one the earlier slide, it looks like those are kind of defects that you see in the
which one are you saying?
blue
The
and the middle.
the lamellar one?
Yeah.
Yeah. Yeah. I mean, lamellar phase is quite common. You can see it in many different contexts, right? So it's sort of, yeah.
So you got that sort of
The catenoid, yeah.
catenoid structure. Could you attach to the end of it, say, and make a membrane out of it, yet another kind of rod, so that you made like a bilipid, like a two-membrane with a hole through it?
Actually, the bilayer thing is what we initially began with. In the sense, if you take two rod lengths which are exactly half, delta L by L is 50%, then the two short rods will climb up on each other to pretend like a long rod.
But I was wondering if you can attach to the perimeter of the catenoid
A flat sheet.
a flattened sheet, maybe by using another
I mean,
virus.
initially, that's how it forms. You start with the flat sheet, which then sort of rises and makes a catenoid. So, and this happens over, I mean, depending on which part of the phase diagram you are. I mean, there's a fully developed catenoid phase where as soon as I inject in the glass chamber, anything that exists is a catenoid. But then if you go, as you approach that transition, there will be times when you have flat membrane which over days becomes catenoid. So there will exist a time point where you have
So you
both.
don't have regions where you have both coexistence of flat membranes and catenoids.
No, it never happens. Either it's a fully developed catenoid phase, or you have these membranes which are sort of bent, Pringle-like, but not Pringles completely, and then they become catenoids.
Then the other where you got the 2D crystalline.
Yes.
Have you looked at the melting transition there and looked at the various order parameters?
Not really. We are looking into it now.
It looks like a nice system.
Yeah. I mean, particularly if there's some exotic phase that exists,
You
or
haven't looked at like the
Yes.
orientational order and so forth?
yes. No, we haven't. I mean, there was only so much I could fit in one postdoc. So.
So it looks like a nice. How big can you make those? How big can you make those crystals?
Unfortunately, so it's limited by how large a membrane I can assemble,
exactly.
right? And so the largest I have seen is 200 particles by 200 particles. So it's just, it's not, and the reason being, I've shown you really beautiful pictures, but it has been sort of, with optical traps we clean up the membrane. So there is a lot of stuff which I think it's because of the fact that the rods are so chiral that you have these defects, and then it cannot coalesce with the membrane and cause trouble. Like, for example, I've only shown you where coalescence proceeds smoothly, but actually the crux of the problem of our membrane assembly is this. So you have these two, So if you have membranes of the same handedness, then there is a huge problem, which is that coalescence just doesn't complete, it just ends up in a line defect. And that's why we cannot grow infinitely large membranes. But we would love to do that, so it's a work in progress. Yes?
And so in the horseshoes that you showed,
Yes.
the binary system?
Yes, it's
So
bidisperse.
is there any difference on the inner and outer
No.
curvature, those are nothing in terms of composition?
I mean, so how do I go here? Okay. That was the problem. We just couldn't make any sense of horseshoes because, so here, sorry, I'll have to go fast. So here, only one kind of rod is labeled, right? So a lot of signal is in the horseshoe, and then there is nearly no signal outside. So in that sense, compositionally, purely long rods here and then purely short rods in the background. But to nail down the composition right at the interface is difficult with just fluorescence microscopy. We need different technique to talk about that. Yes.
So finally, what sets the size of this thing? Is that understood? Like the size of these things that you will get finally?
I mean, we wrote some sort of phenomenological Frank free energy kind of terms, and it's set by the competition between chirality and the line tension between the two kinds of rods, right? I mean, this guy and that guy, but we don't have an analytical expression for it. If that's what you are looking for.
So the free energy thing is not completely understood.
Yes, yes, in that sense, yes.
So that is for the clusters. For
Yes.
the overall sheet,
For overall sheet, you mean
the larger sheet.
Right.
And these are the
inside,
clusters
right,
of
right,
that.
right.
Even for the overall sheet.
I mean, for overall sheet, there's quite a bit of theoretical work from Bob Meyer and his group about understanding the twist penetration depth and things like that. So there, it's much easier to write down just the Frank free energy, and because in this you have to have, in the cluster system, there is an order parameter for the two kinds of rods, and then you have to account for the tilt differences and things like that. So it's more complex.
So if you look at the size, if you make a suspension of these
Yes.
and look at the size distribution of these discs on membranes,
Yes.
so do you find a polydispersity or there is a large polydispersity?
You mean just one component membranes? I mean, it's just one component membranes, it's all kinetically limited. There is no equilibrium size distribution because you have formation of defects and things like that. So it's all in that sense out of equilibrium. Yeah.
Can I ask a very
Yes.
simple question from different background? So when you talk about Gaussian curvature,
Yes.
as you know, there is a theorem called Gauss-Bonnet theorem.
Yeah, Gauss-Bonnet theorem tells you what kind of curvature you would get depending on the metric of the right.
So have you checked any of these, if any of these defects are topological defects, things like that?
No, we have just started to look at the catenoid phase and think about that. Yeah, I mean, we would like to measure the Gaussian curvature modulus, right? And it's really hard to. There is no measurement in the lipid bilayer literature, and in this system it should be easier because of the length scales, but there is no straightforward way to measure the Gaussian curvature modulus.
Oh, you have not, but I thought that you calculated because you said it's negative Gaussian curvature.
So the magnitude of Gaussian curvature is negative, but you want to measure the modulus, right? The rigidity of that term. So yeah.
So let's thank
Okay,
Prerna
thank
for
you.
a great talk.